Hello and welcome to this video lecture about the rank-nullity theorem, one of the most important theorems in linear algebra. So before we talk about the rank-nullity theorem, I would like us to do a very quick revision of what we discussed last time. First of all, linear independence. You see these two vectors here, these two vectors on R squared on the two-dimensional plane. These two are linearly independent, unlike these two, which are not linearly independent. So what's the difference? In the second little figure, A and B are on the same line, whereas in the first figure, A and B are not on the same line, and they span the entire R squared in particular. Likewise, you see here in the three-dimensional space. These three vectors are like this. Maybe the sketch is not ideal, so they're like this. They point to different directions and none of them are collinear with any other one. They're not like this. They're like this. And I cannot imagine a sheet of paper and contain all three of them within this sheet of paper. It is impossible. One of the three will be outside the sheet of paper. If you put it like this one will be outside. If you put it like this, then this vector will be outside the plane. So I cannot contain all these three vectors in a plane which is two-dimensional. That's why we say that these three are linearly independent. A more specific example, now take these three vectors A, B, and C. Here we will have to use the definition of linear independence. The question is whether these three vectors are linearly independent. And as a hint, I'll tell you that if you do 2a minus b minus c, you will get the zero vector. If you don't trust me, do it yourselves. So this is a, this is b, this is c. If you do 2a minus b minus c is equal to 0. Are these vectors linearly independent? No, they aren't. Exactly because of that. This is according to the definition. Next, take these three vectors, and these three vectors are two-dimensional. Are they linearly independent? I will rephrase. Can they possibly be linearly independent? We said they are two-dimensional, and there is three of them. They cannot be. Why? Because the dimension of R squared is equal to 2, which means that in R squared I can only find up to 2 linearly independent vectors maximum. So now, since they are not linearly independent, it means that I can find three numbers, lambda 1, lambda 2, and lambda 3, and not all of these three numbers will be 0 at the same time. At least one of them will be non-zero, such that lambda 1a plus lambda 2b plus lambda 3c is equal to 0, since they are not linearly independent. And this is based, what I'm saying now is based on the definition that we introduced in the previous video lecture. This much about linear independence. Let's have a look now at a few definitions related to linear maps. So first of all, the kernel of a linear map is the set of solutions of the equation t of u is equal to 0. This is what defines the kernel. All these points that satisfy t of u is equal to 0. And it is extremely important to remember that the kernel of t is a subspace of u. The kernel of t is a subspace of u. I would like to draw your attention to this notation I have used here. T is in L calligraphic of u, v. This simply means that t is a linear map, is a linear function from u to v. We write it like this because we're a little lazy and we don't want to write t is a linear map from u to v. Next, the range or the image of a linear map, t from u to v. What is the range? It is the set of all possible values that I can get from t. Mathematically, the range of t is the set of the values t of u, and I'm taking my u's from the set u. It is all the values I can construct, I can make, I can take from t using points in u. The definition of injectivity is very important. So what is an injective map, or also known as one-to-one? A map is injective, a linear map T is injective, if we can use it to separate the points of U, of the set U, by looking at the images through T. To put it differently, because I like to explain things in different ways, so another way to say exactly the same thing is that if T of U1 is equal to T of U2, then U1 is equal to U2, which means, and that's important, it is impossible to have that T of U1 is equal to T of U2, whereas U1 is different from U2. You can always distinguish the U's, U1 from U2, by looking at their images. And there is a very useful criterion when it comes to injectivity. There is a way to tell whether a linear map is injective. Look at the kernel. Look at the kernel of T. If the kernel of T is the set that contains only 0, then and only then T is injective. If T is injective, the kernel is trivial. If the kernel is trivial, then T is injective. And last but not least, surjectivity, or the map being, as we say, onto. It means that my linear map T from U to V covers the entire V. To put it differently, the range of T is equal to V. And this brings us now to the rank-nullity theorem. The rank-nullity theorem states more or less, approximately, the following thing. It says that the larger the kernel of a linear map, the smaller the range. If a linear map T has a large kernel, it must have a small range. If it has a small kernel, it must have a large range. And I have sketched this little seesaw here. So if the kernel is small, the range is big, and so on and so forth. Of course, this is not a proper statement of the theorem. I'll give you a proper statement in a moment. But this is what the theorem says in very simple words. Also, the rank-nullity theorem puts together in the same sentence it puts together in the same sentence the kernel and the range, which we have studied so far entirely separately and without any obvious connection to one another. So now the kernel and the range come in the same sentence. So if I know something about the kernel, I can draw some conclusions about the range. If I know something about the range, I can draw conclusions about the kernel. That's why it's very useful. The rank of a matrix now that we are about to define is one of the most important concepts in linear algebra. Why is it important? Because it can be used to address and solve lots of problems in engineering, in statistics, in machine learning, of course in control theory, of course in estimation theory that we are studying in this module, but the rank is something we encounter in absolutely many different engineering problems and disciplines. And third, the rank-nullity theorem establishes, as I said before, a relationship between the kernel of a linear map and its range. And this is the first definition we need. It is called the rank-nullity theorem. What is the nullity of a kernel, or if you like, what is the nullity of a matrix? The dimension of the kernel of T is the nullity of T. Simple as that. Let's try to understand this a little better. The dimension of the kernel of T. So you have the kernel of T. The kernel of T is a subspace of U. Subspaces are vector spaces. Vector spaces have a dimension. I mean, what is it? Is it one-dimensional, two-dimensional, three-dimensional? The dimension of the kernel. The dimension of the kernel is what we call the nullity of T. A few examples. If you take the identity map from U to itself, then we have shown before that the kernel of the identity map is just a set that contains just 0, like this. The kernel of the identity is the set that contains only 0, which is a vector space, trivially. Therefore, the nullity of the identity is the dimension of this point, which is 0. Another example. Take the 0 map. It maps everything to 0. It is a map from U to itself, from U to U. We have shown that the kernel of U is equal to, we have shown that the kernel of 0 is equal to U. It has a huge kernel, it has a very big kernel. The whole U is the kernel. So what is the nullity of 0? The dimension of U, whatever this is. Another example, take T to be an operator, a linear map. We also call these things operators, but we call them here linear maps. So take T to be a linear map from Rn to Rn, and in this case, in this example, n is equal to 2. And say that this is the linear map that corresponds to this matrix 1, 1, 1, 1. Yes, we've seen this before. We showed that the kernel of T is the span of a single vector. So what is the dimension of the span of a single vector? It is 1. The nullity of this matrix is equal to 1. Now, we talked about the nullity. Let's talk about the rank. It is the rank-nullity theorem. What is the nullity once again? The dimension of the kernel. What is the rank? You guessed right, the dimension of the range. The dimension of the range of a linear map T is called the rank of T. And we write rank T like this. Example. Take A to be a matrix, an m by n matrix. And this matrix A is like this. The first column is A1, the second column is A2, the last column is AN. These are the columns of A. A1, A2 up to AN are m-dimensional vectors. What is the range of A? The range of A is the span of these vectors. The span of these vectors. I'm giving you this result without a proof, but I believe it would be a good idea for you to answer the question, why is this so? So take the definition and make sure you comprehend why the range of A is equal to the span of the columns of A. And a particular example here, so take A to be a matrix where this is the first column. So this is A1, this vector here is A1, and this other vector is A2. The span of these two vectors is the range, and what is the rank? Which is the rank of A is the dimension of the range. It is the dimension of the span of these two vectors. The range of A is equal to the span of these two vectors, and this is equal to 2. Why is this equal to 2 and not equal to 1 or 3 or something else? Well, let's find out. We have two vectors. These two vectors can either be like this. They can be not collinear, or they can be collinear. They can be on the same line. I can have A1, this is A1, and this is A2. It is on the same line, so it can be, maybe, that A2 is lambda times A1. I don't know. I'm claiming apparently that in this case my two vectors are not collinear. Is this true, really? So, I mean, maybe the second vector, 1, 2, 1, is equal to lambda times the first vector. Maybe, let's hope not. But if this is the case, it is the same as saying that 1, the first element, is equal to lambda times 1. 1 is equal to lambda times 1. And then from the second equation I have 2 is equal to lambda times 1 again. 2 is equal to lambda times 1. And from the third equation, I have that 1 is equal to lambda times 0. So from the first equation, I can see that lambda is equal to 1. And from the second equation, I can see that lambda is equal to 2, which is impossible. I mean, what is it, 1 or 2? So the assumption here that the two vectors are collinear is wrong. The vectors are not. These vectors are not collinear. This is not our case. This is our case. And they span a space of dimension 2, because I have two vectors, that's why. Right, closing the parenthesis we opened. So what is the rank of A? The rank of A is the dimension of the range of A, the dimension of the span of the columns of A, which is equal to 2. Lovely. Now it's time to state the rank-nullity theorem, because I know what the rank is, I know what the nullity is. Let's put these things together. So here is the theorem. It says that let U and V, let me put this in a little box because it's an important theorem. So let's say that U and V are finite dimensional vector spaces, and I have a linear map T from U to V. The rank-nullity theorem states that the rank of T plus the nullity of T is equal to the dimension of U. To make our lives a little easier, let's call the dimension of U, let's give it a name. Let's call it N. I can tell from this equation, I can tell from equation 89, that I have two special cases. The first special case is if the rank of T is equal to 0. If the rank of T is equal to 0, this implies that the nullity of T is equal to N. So this is case number 1. And the second case is for the nullity of T to be equal to 0, which implies, I mean, if you make this 0, it implies that the rank of T is equal to N. So we said that this is equal to N. The rank of T is equal to N. In fact, these are equivalences. So if the rank of T is very, very small, if the rank is 0, the nullity is very big, is N. And if the nullity is very small, then the rank is very big, it is equal to N. Let's have a look at this example. This is our old friend, this matrix, 1, 1, 1, 1. It is a 2 by 2 matrix. What is the kernel of T? The kernel of T, we did this before, is the span of this single vector. So what is the dimension of this kernel, aka the nullity of this matrix? It is equal to 1. Have one vector, the nullity is 1. So from the rank-nullity theorem, the rank of T, from this equation, the rank of T is equal to N minus the nullity. 2 minus the nullity is 1, which is equal to 1. So I know how big the kernel is. The kernel has a dimension of 1. Now I know, using the rank-nullity theorem, how big the range is. I know that the rank is equal to 1. Here is a little application of the rank-nullity theorem. This is slightly more theoretical, but I believe it is interesting. So take a linear map that is from U to U. Personally, I like to see analogies with matrices. So think of this as a matrix in Rn times n, n by n. I have an n by n matrix, and the dimension of U is equal to n. I have a square matrix actually, okay, I have a square matrix. So what we're saying here is not true for matrices that are not square. So let's have a look at this statement. T is injective if and only if it is surjective. Injectivity and surjectivity are the same thing when it comes to square matrices. That's an interesting observation. Let's see why. So first of all, before we rush into the proof, let's recall what injective means. Injective means something about the kernel. So this has something to do with the kernel of T. And then on the other hand, we have surjective. Surjective means something that has to do with the range of T. What in particular? Okay, since we mentioned it, what is the meaning of a matrix being surjective? It means that the range of T is equal to U. And what is injective? It means that the kernel of T, just a moment, that the kernel of T is equal to 0. So the kernel of T is equal to 0 if and only if the range of T is equal to U. This is what I want to prove. I have kernel and range in the same sentence. That's a no-brainer. I'll use the rank-nullity theorem. So I'm starting with T is injective. What does it mean that T is injective? It means that, as we said there above, the kernel is equal to the set that contains only 0, which is exactly the same as saying that the nullity of T is equal to 0. There are no other spaces that have a 0 dimension. There is only one linear space that has a 0 dimension, this one. That's why these two are equivalent. So the kernel of T is 0, the nullity is 0. From the rank-nullity theorem, equivalently, the rank of T is equal to n. Equivalently, what does it mean that the rank of T is equal to n? It means that the range of T is equal to the whole space U. Why is that? Let's see. The range of T is a subset of U. It cannot be bigger. And now I know that the rank of T is equal to n. So I know that, let's put these things together, the dimension of the range of T is equal to n. So it's like the range of T is a three-dimensional space inside the three-dimensional space. Yes, but there is only one such space, the space U itself. So range of T is equal to U. What does it mean that the range of T is equal to U? It is the same thing by definition as saying that T is surjective, and this is the end of the proof. So this puts together a little bit of everything we've covered so far. And a few properties of the matrix of a rank. So we can prove these using the theory we've done so far. We'll skip the proofs. If you like, you can try to prove these statements by yourselves. They're not difficult. So if you like to prove these by yourselves, feel free to. Actually, this is good practice of the rank-nullity theorem. But for the time being, let me just walk you through these four very important properties. The first one is important. I'll tell you why. Because let's say you have a matrix that is like this. It is 3 by 10. Someone asks you, okay, what is the rank of A? Before you even tell the rank of A, you can certainly say that this is at most 3. The rank of A is at most 3. Why? Because the rank of A is not larger than the smallest dimension. Here the smallest dimension is 3, so the rank of A cannot exceed 3. Cannot be 4, 5, 7, and so on. The second one is that if you put a transpose on your matrix, the rank doesn't change. So the rank of A transpose is exactly the same as the rank of A. The third one is also important. The rank of A transpose A is the same exact thing as the rank of A. And the third one, I want us to stay here for a moment to appreciate what this fourth property is saying. So this says that if A is a square matrix, then it is invertible. Matrix A is invertible if and only if the rank of A is equal to n. So this is a very powerful criterion for invertibility. As we know, not all matrices have an inverse. If not anything, a matrix must be square to have an inverse, otherwise it is impossible. So if I have a matrix, how can I tell whether it is invertible? This property says, look at the rank. If the rank of A is equal to n, then and only then your matrix is invertible. If the rank of A is smaller than n, then the matrix is not invertible. This is a super powerful criterion, and usually we have to resort to something like this to tell whether a matrix can be invertible. So once again, for square matrices only, a square matrix is invertible if and only if the rank of A is equal to n, to its size dimension. We have talked about inverse matrices. We can extend now what we said about inverse matrices to inverse linear maps. So what we'll do here will not come to you as any surprise. So take a linear map that is from U to V. We'll see later that U and V must have the same dimension for the matrix for the linear map to be invertible. Now the inverse of T, if it exists, is another linear map, T minus 1, that takes me back from V to U. So T is from U to V, the inverse map takes me to the other direction, from V to U. And it has these properties. If you compose T with T minus 1, if you multiply them, if you take the product, T minus 1, this gives you the identity map. And if you do T minus 1T, you get the identity map as well. What are these subscripts here? So what is IV? IV is the identity map. IV is the identity map from V to V. And IU is the identity map from U to U. I have written these in gray color because mainly I want you to remember it like this. T minus 1 is I. T minus 1T is equal to I, which is exactly how we defined the inverse of a matrix, in the same way we're defining the inverse of a linear map. A very important fact, T is invertible if and only if it is at the same time injective and surjective. These are synonyms, they are the same thing. Invertible means injective and surjective at the same time. Again, I'm not giving you a proof for this, take it as a fact. For the inverse matrix, now, so I could have stated this for linear maps, but it's easier to state it for matrices. The following statements are equivalent. Again, I'm focusing on square matrices. The first one is that A is invertible. So the properties that follow, in a way, you can think of them as invertibility criteria. Invertibility criteria. You can use any of these, what is most convenient, to tell whether a matrix, I'm giving you a square matrix, is invertible or non-singular. The first one is that my matrix is injective. The second one is that it is surjective. We said injective and surjective are the same thing, that's why they're equivalent. The fourth one is that the rank of A is n. The fifth one is that the nullity of A is 0. And the last one is that the kernel of A is trivial. You can see here some obvious equivalences. For example, this is from the Rank-nullity theorem. The rank of A is large. The nullity of A is small. The rank of A is n. The nullity of A is 0. The nullity of A is 0 is the same thing as saying that the kernel of A is a point, namely just 0. And of course, if I tell you a matrix is invertible, you must conclude it is square, because there are no non-square invertible matrices. A matrix to be invertible, it must be square. There is no other option. So these are good to remember, but in any case, we will use some of these a lot in practice. So for now, as I have said before, mainly I want you to get some exposure to these notions, and then we'll use them in practice and you'll get used to using them. And this is a very nice figure. Before I walk you through that, and this will be the last thing for today's video, so before I walk you through that, I want you to remember really these three notions. One is the notion of a square matrix. A square matrix is like this. It looks like a square. It is n by n. The number of rows is equal to the number of columns. It is an n by n matrix, or as I have written here, m is equal to n. We are talking about matrices A that are in m by n, have dimensions m by n. So we call the matrix square if it is n by n. It has the same number of rows and columns. If a matrix is extended like this, it is wide, it has more columns than it has rows, we call it a fat matrix. And if it is like this, if it is tall, we call it a tall matrix, if it has more rows than columns. In the middle, you see that A is invertible. A is invertible is the same thing as saying that A is surjective. When it comes to fat matrices, A being surjective is the same thing as the rank of A is equal to M. Okay, this is impossible to remember, I understand, but I want you to have a look and see how you can think of how you can use it, really. So have a look at this equivalence. A is invertible is the same as the rank of A is equal to M. Well, that's very useful. Take the rank of A, compute it, see is it the same as the number of rows of A. If it is the same as the number of rows, then my matrix A is surjective. Does A happen to be square? If yes, then it is invertible. There you go. The rank of A is equal to the number of columns. From the Rank-nullity theorem, the nullity of A is equal to 0. Okay, which means that the kernel of A is equal to 0. Which means that A is injective, as we discussed before. Now A is injective, right? Is my matrix square? If it is square, A is injective is the same as A being invertible. So mainly now I'm explaining to you how you can use this diagram. I trust you will not be quite able to memorize it now, but the point is not to memorize it, the point is to be able to go back here, have a look and say, okay, I want to prove that my matrix is invertible. What do I do? Maybe it is convenient to check that it is surjective. Maybe it is convenient to find the rank and see what the rank is. Also, another important thing, if the matrix is not square, if we're not in this box, we might be on this side that the matrix is tall, then there is no way that the tall matrix can be invertible, but maybe my tall matrix can be injective. When is my tall matrix injective? If the kernel is 0. Equivalently, if the nullity is if the nullity is 0. Equivalently, if the rank is equal to the number of columns. So my tall matrix can be injective. Alright. What if I have a fat matrix? If I have a fat matrix, maybe it can be surjective. When is my fat matrix surjective? If the rank of A is equal to the number of rows. And if my matrix is square, then if my matrix is square, it might be invertible. When is my square matrix invertible? I can check for surjectivity, I can check for injectivity. Either way is fine. I have written here about the left inverse and the right inverse. These are very interesting and useful concepts, but I don't want us to go there because we will not use them in the module, and this is not a general linear algebra course. It is rather a crash course to get you up to speed to be able for us to do control and estimation theory afterwards. So that's the end of today's video. Next we'll talk about linear equations, which will be the last part of our discussion on linear algebra. Until next time, Thank you very much for watching, and goodbye.